So one of the best ways to determine when or how a material behave like a viscous fluid or an elastic solid is to do dynamic mechanical testing. Sometimes it's referred to as DMA or dynamic mechanical analysis. And what it is essentially it's a test where you have this kind of cylinder and it's filled with some type of polymeric material. And you have this other kind of plunger that goes into the cylinder and we rotate at a certain frequency omega. So we apply a sinusoidal stress at variable frequencies. So the sinusoidal stress. Now the material will experience a resulting sinusoidal strain and thereby a stress on our system. So the material exhibits this stress where there's part of it that's in phase with the applied stress, so the applied strain effectively. So this sine omega. So we have a component that's in phase, and we have a component here that's the cosine that's out of phase. So if I'm in phase, I'm getting like this instantaneous response. So that in phase is essentially our elastic response. Our out of phase component is our viscous response. So that is going to be our viscous response. This will be our elastic response. So we can start to define some variables, and specifically using our stress and strain expression. So we can define our storage or our elastic modulus, which is again our in-phase component. So the storage modulus, E prime, sometimes you'll also see G prime, that's going to be our elastic contribution. And our loss modulus is going to be G double prime or E double prime, and that is our viscous response. And you can see some other definitions as well. And a loss tangent, which is different. Now, we can analyze these responses in this dynamic mechanical test or dynamic mechanical analysis. So what you're seeing here is a curve as a function of frequency of our G prime and our G double prime. Now, the curve that's higher is the dominant response. So at high frequencies, to the right here, my G prime, my storage modulus is larger than my loss modulus, so this is elastic. And this should make sense because we said previously at very, very high strain rates or frequencies, we should expect a solid-like response. So, and we should be viscous at very, very low frequencies, which is what we see here. So viscous. So you see kind of this difference in behavior. This crossover point is called our relaxation frequency. And we can actually deduce, so this is our omega star, is our relaxation frequency. And we can actually call this our, if we do 1 over omega star, that's our relaxation time, tau. It's not shear stress. I know it's confusing, but it's how it is. Now, you can draw this same curve. So if I were to do, I could replace omega with strain rate and it'll look exactly the same. If I were to plot this versus time, this would be very, very low time. This would be very high time. Because at high, long times, I'm going to behave like a viscous fluid. At very, very short times, I'm going to behave like an elastic solid. Same thing, and this would be your relaxation time. Same thing for your temperature, and this would be low and high, and this would be your TG, your glass transition temperature. But we'll get into glass transition temperature in a bit. So you can plot this for very, very different types of x-axis, but again, it's the same time temperature equivalence, and we'll see essentially how our system responds. We have composite mechanics here, but we're not going to go into that in this particular course, but we'll see it in another course coming soon. Machine design, most likely. So, or advanced mechanics materials and advanced polymers. All right, now we're going to get finally into the plastic regime and talk about yield criteria, and we'll see you all in the next video. Thanks. Bye.